Greetings. This is a lesson about the efficiency of heating and cooling systems. The first thing we need to talk about is how traditional heating and cooling systems work, which is they're controlled by a thermostat. Thermostat comes on, the heating or cooling system runs for a while, and then it turns off. And what happens is that what we're doing is we're heating up a heat exchanger or cooling down a heat exchanger. And we have that takes a certain amount of time. And then we run it for a certain period of time. And then when the thermostat turns the system off, then that heating or cooling heat exchanger changes its temperature, and energy is lost with each one of those cycles. And that's one of the major losses that we're dealing with, one of the major problems with efficiency. So what we would rather do in a perfect world, we would have modulation, which means we could control the speed of the fans, we could control how fast gas was coming into a burner, we could control the speed of a circulator that was circulating hot or cold water. And we could do that so perfectly that we could match exactly the rate at which a building was either being heated up or cooled down. We would have an exact match, and the heating or cooling system would run all the time. That would be kind of perfect efficiency. The other thing that would indicate a kind of a perfect efficiency is, a very small temperature difference between the thermostat set point and the heating or cooling fluid. So just keep that in mind when I talk about the principles and the operation of these heating and cooling systems and how that affects the efficiency. So let's look at combustion first. We have combustion here, and we have a heat exchanger that has a fluid. And we're bringing fluid back from the heat emitters, circulating it through this heat exchanger, and then we have a warmer fluid coming out. Now, the AFUE, or the annual fuel utilization efficiency, is output divided by input. The output BTUs divided by the input BTUs. And there are a number of different efficiencies. The AFUE is only one of them. We could measure the efficiency of the gas burning, what efficiency that is, and it's probably something like beyond 99.5. We could measure that right here, but if we measure the wasted heat right here and calculate the efficiency from that, that's called the steady state efficiency, and we can do that with a combustion analyzer. And then, if we went all the way out, we can do it, we can measure above the flame, we can measure outside the heat exchanger, or we could go all the way out to the heat emitters and, do some calculations and some measurement and actually find out what the system efficiency was. That's very rarely done. But, the efficiency is going to be higher if we can control the gas coming into the burner, and make it just as much as we need to make up for the heat that's being lost. And we would have to control the air too to make this combustion as perfect as possible, so a lot of heat wasn't going up the chimney. And then we would have a flow control here that would give just the right flow rate also. So you kind of get the idea of how this combustion works. Now, when we're looking at the refrigeration cycle, that's a little bit more difficult to understand because, instead of, converting fuel to heat, what we're doing here is we're just moving air from the outdoors to the indoors in the wintertime and moving heat from the indoors to the outdoors during the summertime. So these coils, this outdoor coil and this indoor coil, what they're doing is the coil either gives heat or takes heat from the air that's moving through it. And so how do we measure the efficiency of that? Well, in the USA and not in other places, we have these three measurements: EER, SEER, and HSPF. So this is energy efficiency ratio, seasonal energy efficiency ratio. These are two cooling efficiencies. They're measured in BTUs per watt hour. BTUs is our American unit of heat. Watt hours is we use for electricity. And so we get a number like, the EER might be something like 12, the SEER might be something like 17, 20, something like that. The reason for the difference is that the EER, measures the efficiency at the peak load, really at the design load, which is a severe temperature and relative humidity, while the SEER is measured at a range of temperatures and relative humidities. That's why it's a higher number. The HSPF, we have to assume a certain temperature, a certain outdoor temperature to get the HSPF. I can't remember exactly what it is, but the actual heating efficiency of a refrigeration device is going to be way higher in Miami than it is in Minneapolis, just because a moderate climate or a mild climate, you're going to be able to heat and cool with very moderate types of temperatures, whereas in Minneapolis, the temperature difference between the thermostat set point and the delivery temperature is going to be much higher. So you got BTUs per watt hour. We can make some choices based on these numbers. The higher the EER and SEER you have, the more efficiently that air conditioner is going to run. And so that's what they're used for, these efficiencies. But there's also a more universal type of efficiency that's called the COP, or the coefficient of performance. And that's like output in watt hours divided by input in watt hours. Now you remember over here, we've got same thing, output divided by input, but we're always, the output is always going to be less than the input, because we're never going to get all the BTUs that are locked up in that fuel. We're never going to be able to utilize all of them. Whereas here, we're just moving heat between one place and another, we might be able to move as much as 5 BTUs for every 1 BTU we expend in terms of electrical energy. But we actually measure electrical energy in watt hours, which are just a function of they're really the same as BTUs, and the conversion factor between watt hours and BTUs is that there are 3.412 BTUs per watt hour. Okay, so the COP is the output in watt hours over the input in watt hours, and if you divide watt hours by watt hours, you end up with a dimensionless thing, which is what COP is. COP would be 1.5 or 2.5 or 4 or 5, just a number like that. It would tell you how much heating or cooling energy you would get from a single unit of electricity. That's the way that works. So I hope that gives you an idea of the operation and the ideal operating conditions that we're shooting for in terms of both heating by combustion and heating and cooling with a heat pump.